Okay, let's start. So I'm Chenglin. So I from Kuaishou Technology. I based in Shenzhen. So today I will talk about the recent works with using deep learning techniques to solving the cocktail party problem. Before that, I first will introduce what is cocktail party problem. So as we know, we are in a party. So there are many people. We talk to our friends. But we still can hear our friend's voice. Then we overlook others talk, or we overlook the background music. So we only focus our attention to our friend's voice. So we call this is the cocktail party effect. So the Professor ISCSLP do the experiment to show the effect. But now no machines has been constructed to do such kind of things just like human. So in this work, in this talk, we would like to introduce us the recent progress in speech separation or speech extraction to solve the cocktail party problem. So we would like to formulate the cocktail party event in such kind of these figures. So we have the talk voice will be directly into the sound. Will be directly captured by the microphones. Also the voice will be reflected from the words. This reflection sound will also be captured by the microphone. So this is the vibration. We also have some other talks. We call this is interference speakers. We may also have some other noise, for example, the air cons or the other background noise. Sometimes we also have different kind of microphones, so they may have the channel distortions. So if we because due to the COVID-19, most of the time we are doing the online conference or the real-time communication. So we also has another scenario which is echo. So we also have the echo cancellation. So for different kind of scenarios, we may have different techniques. For example, if we only get the speech, we want to remove the noise, we have the speech enhancement. So the speech enhancement will remain all the speech of different talks. So we also have the speech dereverberation, which is we remove the reverberation from the reflections. We also have the speech separation, which is the main topic of this talk. We are going to separate the speech of each talk into an individual channels. Before we start to introduce the techniques, we would like to talk about some background of the speech separation. So speech separation aims to let machines have the same auditory ability as a human in a cocktail party environment.
She has no idea whether it's Russia, China, or anybody else. She has no idea.
So we have so speech separation. What speech separation?
Whether it's Russia.
Sorry, it's automatically plays the video. So speech separation try to recover all the original speeches of each talk. Then the separated speech will be in an individual channels. So for example, we have this
She
debate.
has no idea whether it's Russia. She has no idea whether it's Russia, China, or anybody else.
I am not quoting
myself. No idea.
I am quoting
Hillary, you have no idea.
17 do you doubt 17
our
military
country has
and
no
civilian
idea.
agencies? Well,
yeah,
he'd rather believe Vladimir Putin.
So this is an old demo which was done by me in 2017, I remember. So we have the debate of Trump and Hillary as well as the video. Actually, we check the speech part. Then we do the separation. We try to separate the speech of each one. Here is the result of Trump's voice.
She has no idea whether it's Russia, China, or anybody else. She has no idea. Hillary, you have no idea. Our country has no idea. Yeah, I doubt it. I doubt it.
So here is the separated voice of Hillary.
I think it's time you take a stand. I am not quoting myself. I am quoting 17 do you doubt 17 military and civilian agencies? Well, he'd rather believe Vladimir Putin.
So let's back to listen to the video again.
I think it's
She
time.
has no idea.
So here we can see that there is some interrupted speech by the anchors. So we remember this because we are also hear the interrupted speech in the Hillary's channel, right? So we will talk about this later.
She has no idea whether it's Russia, China.
Sorry. So for speech separation, we divide it into the multi-channel and the single-channel one. For multi-channel, we have additional information which is spatial. We have the angles of where the source comes from. So with this information, we can improve the performance by forming our beam to the target to the source. So for the single channel, which means we only have one channel of mixture recorded speech. So with this speech, we don't have the spatial information, which is the direction of each of the top. So we can the information we can use is only the signal itself. So for the single channel method, we are trying to using the recorded signal as input to do the separation to get the estimated speech of each of the speaker in the mixture. So so as we say, why do we need to do the speech separation? Actually, for many real-world applications, we need to do speech separation. For example, human-machine interactions. For example, we have the robotics in the shopping mall. There are a lot of noise. Also, maybe some inference speaks voice are being recorded. So also for the hearing aids, for the teleconference smart device. So if we don't solve the problems to handle the multi-target scenario, then the usage of these real applications will be limited. So here I will briefly introduce the history of speech separations works. Actually, speech separation has been studied for many years from the auditory models, which we call the computational auditory scene analysis. They use the pitch continuity, vocal continuity, temporal continuity, harmonics, common onset or offset. So they use these information to do the separation. After that, we have the decomposition models, which is the signal processing based method, for example, the ICA, AMF series. After that, we have the statistic models, which is the GMM. In recent years, we moved to the deep learning. Actually, today we mainly focus on the deep learning techniques to solve the to do the speech separation. So here is the performance of the recent works on what's the generative mixture database. So you can see from 2016, we achieved 10.8 SDI improvement. So SDI means signal to distortion ratio. Until now, we can achieve 22.4 dB improvement. So today we mainly focus on this kind of techniques. So for speech separation, we mainly actually here we saw source separation. Actually, source separation including several categories. The most important one is the speech separation. So source includes a lot of signals. So if different kind of signals combined together, we can divide them into each individual channels. So we say the speech separation means we separate the speech of two talks, which is a hard, actually is a hard task. So we divided the speech separation into frequency domain and time domain. What means by frequency domain, time domain? Frequency domain means we do the short time Fourier transform to get the magnitude and the phase spectrogram. So for the time domain, that means we use the signal itself as the input to do the end-to-end learning. So before that, we will introduce a concept which is auditory masking. So human has the masking effect, which is we only if the signal of is lower, the energy of the signal is lower than another one, so we can only hear these higher energy signals. We cannot hear the lower energy one. So here is the in the frequency axis. If we call this as the simultaneous masking. So for the temporal dimension, we also have this masking effect, which is the temporal masking. So with this masking effect of human, so how can we invent a mask which is to filter the voice of others only to focus on one of them? So we so we developed the ideal binary mask, which is we giving a value to each of the time frequency being either 0 or 2 or 1. So this is a hard mask, either 0 or 1. So here is the performance. Here we use the ideal binary mask. So here is if we use this ideal binary mask, so here is how is the performance of the separation.
Bismarck serves as a trade and shipping point for an area of large mechanized farms.
So we can hear some interface, which is da da da. Actually, because this is the hard mask, which is either 0 or 1. To improve the quality of the signal, we invent the ideal ratio mask, which is a softer one. For each time frequency being, we have a value which is between 0 and 1. So we have this. Let's hear the voice.
Bismarck serves as a trade and shipping point for an area of large mechanized farms.
So here you can see the quality of the signal is much slightly better. So we also have some other masks. If you are interested, you can see this paper. They actually summarize several different masks. So for the frequency domain speech separation, previous works mainly focus on the form the separation into 3 different categories, which is we direct spectrogram estimation, which means we do the feature mapping using a neural network with a regression task. It means we have the signals in, we do the short-time Fourier transform, we get the magnitude spectrogram and the phase spectrogram. Then we do the neural networks to estimate the spectrogram of each talk. Then we have the clean magnitude spectrum of each talk as a reference. We calculate the errors between the estimated and the clean one. So we do this feature mapping. Another one is we do the mask estimation, because previously we have calculated the ideal binary mask and the ideal ratio mask according to the clean speech. So we can use that as the reference to estimate the mask directly. After we estimate the mask, we can use the mask to filter the magnitude of the original mixture signals. So we can use then we can get the estimated magnitude spectrum of each talk. Then we can use the phase of the original one to reconstruct the signal. So the direct signal estimation, what what does that mean? It means because first we use the ideal binary mask or ideal ratio mask as a reference. Because this mask is not optimal, so it does not estimate the signal itself. So we want to estimate the signal by using a mask inside, which is we have a layer to estimate the mask. The value is contained between 0 and 1. So we call this as a mask. Then we calculate, we filter the magnetic spectrum by this mask, and we get the estimated spectrogram. Then we use this spectrogram to do the to calculate the errors to train the neural network instead of using the mask. So this three methods we call is the traditional one or the conventional one because they don't solve the permutation problem. What is permutation problem? It means we have several outputs, right? Then we have several reference. So how can we calculate how do we assign the reference to the estimated one to calculate the errors? So in this method, they just using the fixed assignment, which is estimated one is calculated with output one is calculating the error with reference one. Output two is calculate the error between with reference two. So they don't calculate the permutations. So this work doesn't generalize well to unseen speakers. So after that, recent works mainly focused on to solve the permutation problems, which is using the energy continuity or using the deep clustering k-means or speaker IDs to form the center of the speaker. Also, you have the permutation inverse training. Have the two-stage one. The first stage is to do the frame level separation. Then the second stage is try to grouping the frames of each separated speaker. So another one is a fixed level assignment in permutation inference training. So later I will introduce all of these kind of works. Another work try to solve is to do the phase estimation, because in the frequency domain we have the magnetic spectrogram and the phase. When we reconstruct the signals, we always using the phase of the mixture signal. So this kind of phase is not optimal. So we have the phase sensitive mask. We have the unfold iterative phase reconstruction. Also, we have the most of work you doing the time domain method to avoid the phase decomposition. Another one is vocoder, which is we have learned the mere features, then we can use the vocoder to reconstruct the mere features into the time domain signals. So another problem need to be solved is unknown number of speakers problem, because during training we always know how many speakers in the mixture, then we have the equal number of outputs. But for the inference, because we don't have the prior information, we don't know how many speakers in the mixture. So if we train with a fixed number of outputs, then we cannot handle the mixtures when the number of speakers is larger than the number of outputs we have. So another work is we try to use the PID. Actually, we can train. One of the solutions is we can train as many as outputs as possible. So in that case, we can handle some of the case. Another one is we do the iterative separation. It means we separate one speak at one iteration. Also the speaker ejection, which means we only focus on the ejection of the target speak by giving a reference clue. So now let's talk about some representative works. For example, the deep clustering. The deep clustering tries to learn unbanding for each time frequency beams. After that, we can use this to estimate affinity matrix. As we know, we have the clean speakers. Then with the clean speakers, we can calculate the one-hot speaker labels for each of the time frequency beams. So we also can get the ideal affinity matrix. So we calculate the errors between the ideal and the estimated one. Then we can train the network to learn the unbandings. After that, after the training, when we do the inference, we can use the k-means to cluster the unbandings together. For example, one speaker's unbanding, we cluster them together, then we form a mask. Then we use this mask to filter the spectrogram of the mixture species. So after that, there is DC++, which is to incorporate the enhancement network after the mask estimation with soft masking. So it means you can conduct the end-to-end training of unbanding and clustering together. Another work is to try to use the ideal mask or KB to form an attractor. This attractor is like a center of the speaker. So we use this center as one of the information we can get the speech of this speaker. Then use this information. Use the attracted speech. We can calculate the loss, and then we can train this network. As we progress to show that the conventional regression method or the masking estimation method, they're using the neural network to estimate the output directly without doing some speaker centering or the clustering. So this works tries to improve the traditional one by solve the permutation problem with permutation invariant training, which is to calculate the loss across all the permutations, then get the minimal one. With these minimal errors, we use this permutation to assign the labels to train this network. So this network, work using the feed-forward and the convolutional neural networks. They cannot capture the sequential information. So the input is a context of the windows. There is a problem is the permutation may be switched across the context window. So they further proposed the bidirectional ISTM as a network to learn the sequential information to force the output of this one is belonging to a single speaker. So the same permutation invariant training is calculated. Because here we still calculate the loss frame by frame to get the final by sum them together to get the final loss. So without consider the context information. So after that we consider to propose a constrained permutation invariant training, which is we consider a context of the output to calculate the errors between the reference one and the estimated one. So in this case, we can have the context information to force the context windows to be continuity. With the bidirectional ISTM and the gradient ISTM to learn the features, then we can capture the long sequential information. So so the output of the speech of each speaker will be improved. After that, we also propose to using multitask learning, which is we use the information of labels to show what categories of each time frequency belonging to. For example, for this each time frequency being, we have 3 categories. Here it's the silence. Here is a single speak. here is the overlapping speech. So we use the softmax to classify whether this type of speech is belonging to one of the three. So we use this multitask learning to further improve the performance and explicitly to tell the network how to estimate mask. For example, for the silence part, we can giving a small value of just a 0 as the mask. For the single one, we can giving 1 or approach to 1. For the overlapped part, we giving the mask between 0 and 1. So it can help the network to learn the mask. Until this work, we only focus on the improvement of magnitude spectrogram. So even though in this PIT method, we use the phase-sensitive mask to compensate the phase difference between the mixture speech and the clean speech, but it is still not as good as the clean phase. So in this work, it proposed multiple iteration phase reconstruction method. As we know, we have the separation of each speakers. So we have the mixture speech. We use the phase of the mixture speech to reconstruct the signal. Then we sum all of the separate speech together. Then we get the errors between the input and the sum of the estimate one. We get the error. Then we divide the error by the number of speakers. Then we compensate each of the output with these errors. Then we do the short-time Fourier transform again to get the refined phase information. Then we do the signal reconstruction again. Then we get the signal. So we do the several rounds. Then we finally can improve the performance. But then here has a problem is we in this case we only can handle the mixture is only contains the speech of multi-talks without noise and vibration. If noise and vibration is occur in the mixture, then this method cannot be worked. So this is so why we in the following work, so we want to use the time domain to do the end-to-end modeling. So also in the frequency domain, it has a two-stage method, which is we do the separation first, then we do the second round grouping. Which is, this grouping is try to clustering the frames of the same speaker together. So so with this two stages, then the performance can be improved. So when we evaluate on the work situation to make a database, then we can see as a two-stage mesh that actually achieves significantly better performance. So if we do the multi-run in the phase reconstruction, then we also can improve the performance. So here, if we do the constraint, which is we use the context in the loss function, we can further improve it compared with this one. So this is the deep clustering method, which is different from the method to do the direct mask estimation. So in this work, so we also define error to show how is the separation quality of our system. Because otherwise we just see the signal to distortion ratios, but these numbers cannot show some case, which is we cannot know is this separate speech has other speakers voice, which is we call the insertion error. Here corresponding to a deletion error. Also sometimes is a substitution error. So we calculated this frame leakage error rate, which is similar to the word error rate in the speech recognition. So with this we can know that with the context inside the loss function, we can significantly improve the performance to reduce the deletion, insertion, and substitution errors. So actually, in many real applications, for example, our online conference applications, we don't tolerate the deletion errors. It means the speech of the speaker's voice is missing. Then others cannot listen what he's talking about. This cannot be tolerated. So we also call this is the oversuppression problem. So with this FLER, we can have the individual deletion error, insertion error, and the substitution error. Then we can evaluate how is the performance of our system to set a threshold to our real applications. So also we do subjective evaluation because sometimes when we see the SDI is better, but the perception quality may be not as good as the lower SDR systems. So with the listening test, we can see the proposed system is better than the baseline. So here is some examples of the comparison between the baseline and the proposed system.
Bismarck serves as a trade and shipping point for an area of large mechanized farms.
So you can see one of the speaker's voice is still remains in the output in the output. So there are many insertion errors.
Bismarck serves as a trade and shipping point for an area of large mechanized farms.
So actually in this one, the insertion errors is reduced significantly. So here is we can see this is a deletion error, but here we can see this method doesn't have this kind of deletion errors. I just said, we are trying to use phase iterative phase reconstruction to improve the phase part. So another work we are trying to do is to do the time domain, which is we use the signal itself as input, then the output is the separate the signal. So we use the encoder and decoder to replace the short-time Fourier transform and the invert short-time Fourier transform. Then this network-based encoder and decoder doesn't decompose the signals into phase and magnitude. So this kind of work done has phase problems. Then it means without the phase problem, this method will improve, will achieve better performance. So most of the time domain speed separation systems adopts this kind of framework using the encoder to encode the time domain signals into the feature implementation. Then use a separator to explain masks. Then use the mask to filter capture the feature implementations. Then finally use the decoder to reconstruct the signals. Recently, many of the works have been done in the time domain speed separation. They mostly try to improve the network structures. For example, use BRSTMs, temporal convolutions, dual pass, or the multi-head attention. Also, they try to use the two stages, which is in the first stage, they try to use a good speech encode and decode. Then after that, they fix the encode and decode to learn the separator. Also, is another is using the fixed permutation to assign the labels to calculate the errors. Also, the hybrid systems, which combine the information from frequency domain and the time domain. Also, the multiple iterations, which means we do the separation first, then we use the separated output together with the original mixture, then do the second run separation. Then we can do several run iterations, so then we can further improve the performance. Also, the pre-training for robustness, because in the time domain method, we the encoder, the speech encoder mainly learns from the data. Then the data distribution may be affect the performance. For example, if we train in one kind of data set, and then we test on a different data distribution of real world signals, then we can the performance may be the performance becomes worse. So we can use the pre-training or unsupervised training or self-supervised training using a lot of real-world data to initialize the models. Then we can improve the robustness. But also another work is to try to generalize the model trained in one language to other languages. As I just said, most of the works are adopted the encoder separate and decode frameworks. So they replace the network structures, for example, bidirectional STM or stacked temporal convolution networks. In the second stage, in the two-stage method, they try to use train an encode and decode first, which means they use the clean speech and together with the mixture speech as input. Then they use the softmax to get the ideal masks. Then they train the encoder and decode. After they will train the encoder and decoder will train, then we fix them. Then we train the separator. After the whole network is trained, then we can have our final speech separation system. Also, we can try to fine-tuning the encode and decode again. So another work is to do the label assignment. In the permutation invariant training, as we know, we calculate the errors across all the permutations. So we find the permutation with minimal errors. But sometimes the permutation assignment for the same input may be different from epoch to epochs. So it means in this training epoch, the assignment output 1 is to reference 1, output 2 is to reference 2. But in the next epoch, the output 1 maybe go to the output the reference 2. The output 2 maybe goes to the reference 1. So the assignment changes. So it's not good for the training part. So this work try to study 4 different kinds of label assignment, which is based on the energy-based label assignment. For example, for the output 1, we always output the speakers with higher energy. The second one is the speaker with lower energy. So we fixed off this kind of labels. Another one is a speaker unbanding based one. Actually, we calculate the estimated speech and the reference speech to use the speaker unbanding to do the label assignment. Another one is a fixed label assignment using the permutation from the PIT. For example, we train the PIT with 100 epochs. After that, we use the permutations for all the training data, and we fix them. Then we retrain the system. Another one is we interrupt the PIT with the inserted section of fixed level training, which is we train the PIT first. Then we use 100 epochs of the label assignment to retrain the network. After that, then we use the PIT again to further train the network so we can achieve better performance. So this work is try to combine the information from different domains, for example, in frequency domain and the time domain. So they just combine the features together to do the mask estimation, then estimate the marks in both time domain and focus domain, and then to train the network. So the performance can be improved by combining these two kind of different informations. Previously, we say we using the bidirectional RSTM or temporal stacked temporal convolution networks. It means we want to capture the sequential information. But if our input is very long, the sequential information may be not good captured by bidirectional RSTM or stacked TCN. So some of those works try to use the dual path, which means we use intro and inter module to capture the local local information and the global information. So how they do this is they first do the segmentation by the segment the long sequence into short one by 15% overlap. So after they get this kind of segments, then can form a 3D matrix. Then with that we can do the inter first. We do the inter feature learning along the temporal dimension. After that, we permutate, which is a transpose them. Then we learn across the segment, which is we capture the global information. After we learn this kind of features for each speaker, then we do the overlap and add to reconstruct the time domain nodes. So for this dual path networks, the DPRNA actually use the bidirectional RNA in the intro part and in the inter part. So the gated one means they use a gated mask after this to improve the performance of DPRNA. So the DPNet, which is a dual path transform, they replace the bidirectional RNA with transformers. The GALR, which is they do the local information capture with the bidirectional RSTM. The global one, they use the multi-head attention. So the standard glasses, they try to use the unit structure. Actually, in the unit structure, they in the each layer of the unit, they use the local one, the global one, which is the local one uses RN, and then the global one uses a self-attention. The self-former is similar to the DPNet. They use the transformers in the interpart and the interpart. This SEP-IT, which is the one I mentioned previously to do the separation multi-run. For example, he evaluate the multi-run of DPRN, multi-run of SEP-former. Then it shows if we do the multi-run separation, the performance can be further improved. As I previously I said, the time domain has a problem is we cannot generalize to unseen or different data distributions because we train on a database. Then all of the networks are learned from this database. Then it may not generalize to other database. Also the real world applications. So actually here we propose a system for speech enhancement or time domain speech enhancement. We have we use matrix, the noisy speech and the clean speech. Actually, they are not paired. So for the noisy speech, we can have a lot of noisy speech in the real applications. For the clean speech, we can record it in the silence rooms. So this X and the Y is not required to be paired. So in the supervised, in all of the previous works, we do the supervised learning. We need to have the paired data, which is the input and the clean reference. They are paired. So in this unsupervised pre-training, we don't need to be the data to be paired. So this case is evaluated on the speech enhancement. We estimate the noise part and the speech part. So we use the discriminator and the reconstruction laws to pre-train this network. So this can be extended to the speech separation, which is we have separated for each speaker. Then we can also use this kind of laws. So in the second stage, we do the mixture training. For the mixture training, we still use a lot of mixture noisy data without labels. Also, we have a small amount of data with paired data, so we can further improve the performance. Because this data is also learned from the real-world applications. For example, the noisy data, the unpaired noisy data. So this one can generalize the real to the real applications. Also, we have the mixed IT. For the supervised preliminary training, we have two sources, which each source is clean. Then we have the separation. Then we combine them, or we use one of them to calculate the loss. For this unsupervised one, it means we have mixtures. We try to combine them together to get a mixture of mixtures. Then we separate the individual of the speakers. Then we do the remix. So we have a lot of implementations. We do remix. Then we calculate the loss between the mixture and the remixed signals. Then we can do this self-supervised training. Also, there are some other works to do the pre-training. For example, they use speech enhancement system as initialized to train the network. Actually, this work is not mentioned and not listed here. So here is the performance of the works I talked about. So this part mostly are the frequency domain method, and this part are mostly the time domain method. So we can see the time domain method achieves better performances than the frequency domain. So also this deep class is frequency domain by 2 stages. So actually this some of them is try to improve the network structures. If this kind of network structures is used in the frequency domain method, maybe the frequency domain the performance also improve. So we also conduct another work, which is try to generalize the models from one language to other languages. So we have the global phone database, which is 12 languages, more than 2,000 speakers. So we use 5 languages to train the individual systems. Then we use the rest 17 to as an evaluation. So we also evaluate on the trained network. So for each, for the trained system, if we train individual system with the single language, then it only can work well on the same languages. Sometimes they can work well on the part of language, similar languages, but they cannot. In most of the cases, they cannot work well in other languages. But if we combine several languages together, then the performance can be significantly improvement each of these languages. Then for these unseen the 17 languages, they can also achieve the best performance. So yeah, I want to say, so if we want to design a general system to handle different case of scenarios, for example, some speakers can speak binary languages or trig language. So we can use this kind of language augmentation training, which is combine the several different languages to train a system to generalize real to unseen languages. Another problem in speech separation we want to solve is unknown number of speakers. So we say during training we know how many speakers in the mixture because we are the data is simulated. We know how many species in each mixture we have added. So, but during the inference for the real applications, we cannot know the number of speakers. So what we can do is we can do the iterative separation. In each stage, we only output the speech of one speaker. So we have the rest residual rest masks. So this residual mask and the input string is used to do the second round estimation. So we do the several round, and then we can get the separation of each speaker. Actually, we have two different kind of stop threshold. The first one is we can set a threshold to the mask. If the mask is all zero, it means there is no rest speaker need to be separated, then we can stop the iteration. Another one is we can use a threshold to set the number of iterations we conducted. For example, we only want to get 3 speaks, then we do 3 iterations. Because most of the case, for example, in the conference, when speakers overlap, most of the case are 2 speaker separation. Some small portion are the 3 speakers. So, for example, we can say we do 5 round iterations, then it may be enough for the case we want to get the speakers of all the overlap part. Then we can do some threshold to see how many speech, how many output of silence. And okay, maybe we'll have a break. Then after that, we have the second part. So if you have any question, you can type in the chat, or you can raise your hand. Then we can talk about. Okay, let's start for the second part. So for the second part, I'm going to talk about the speaker detection. Actually, speaker detection is we can see it as a type of source separation. So it only focuses on the detection of the target speakers. So the motivation of speaker detection is to mimic a human's top-down selective auditor attention. So giving the reference clue of the target speech, then we can use the network to learn the to estimate the speech of the target speak. So it's just like our go-type party effect, and to overlook other interference speakers' voice by focus our attention on the interest. So this is speaker detection actually address the unknown number of speakers in the mixture. So also solve the global speaker permutation ambiguity problem because it only focuses on the target speak. So without many outputs, so it's only have one output. There is no permutation problems. So first, we also first consider the frequency domain method. Actually, in the speaker detection, according to the different of reference clues, we divide them into the audio assisted, visual assisted, and the heterogeneous speaker detection. So for the audio assisted one, we first introduce the frequency domain method, which is also we use the short Fourier transform to decompose the signal into a magnitude and a phase spectrogram. And for the reference speech, actually we can record a speech as a in row. So we get the speaker embeddings, which is to categorize the target speak. So with the magnitude of the mixture together with the speaker and embeddings of the target speak, then we use the speaker ejector to estimate a mask. This mask is only for the target speak, so we can get the estimated spectrogram of the target speak. Then we use the phase of the mixture speech. Then we reconstruct the signals. So the one for the frequency domain audio assisted speech detection is the speak beam based, also the voice filter live, and I'll work on the based on the speak beam. So here in the speak beam method, they try to use several layers of feed forward to estimate the weight. This weight is used to get the importance of each sub-networks. So after that, they sum them together. Then use this information to estimate the mask of the target speaker. So after that, we try to improve the framework of the speak beam by several points. The first one is we use bidirectional RSTM to learn the speaker embeddings. Another one is how we combine the speaker embedding information into the ejector of the target speaker. So here we use the bidirectional RSTMs to estimate masks of the target speak. Another difference is in the loss function, we try to use the context information, which is verified effective in the speech separation. So we also use that here to consider the context in the loss functions. As we know, in the speech extraction in the frequency domain method, we are also using the phase of the mixture. So this kind of phase is not optimal. So we also try to propose the time domain one, which is I use a similar speech encoder and decoder to replace the short time Fourier transform and the invert short time Fourier transform. So similarly, we have the speaker encoder to encode the reference speak into a speaker embedding to characterize the target speak. After that, we use the speaker embedding and the embedded coefficient to get the mask of the target speak. Then we use the speech decoder to reconstruct the signals. Here is another work we try to use because here for the speech encoder, we can use several parallel one, each one with different lengths. Then we can have the different temporal resolutions. So combined with them, then we can do the separation. With this loss, with this parallel one, we can improve the performance. Also, we combine the speaker ID loss to further improve the performance. Because sometimes if we only this part we only need to characterize the speakers. Then if we add a speaker ID loss, then we can better learn the speaker embedding features. Another one is we try to use the shared speech encoder. Because in the previous work we still use the frequency domain, for example, the field bank as features. So to improve, make the mixture speech and the reference speech into the same vector space, we try to use a shared speech encoder, which is to transform them into the same feature space. Then with this performance, with this shared one, we can further improve the performance. Another one is we try to study how can we reinforce the attention, because previously we say we have the XT, right? This actually is a pre-recorded signals. Along with the time, the speaker may have the characteristics of the speaker may have a slightly change. For example, we call it sick. Then the characters with the normal one is different. So we can use this kind of adaptive speaker embeddings to reinforce the attention, which is we can do the multi-run. First, we have the traditional one. We have the pre-enrolled speech as a reference to get the speaker embedding to estimate the speech of the target speaker. Then we use this as additional information to the speech encoder to get the better speaker embedding. Also, we can use in the speech separation part, which is similar to the multi-iteration speech separation systems. So here we can the combine of this speaker information is in two different case. The first one is in utterance level, which means we combine with the original pre-enrolled, then we get the utterance level. Here we get the frame level because this ST is aligned with this YT. They are corresponding to each other, so we can have the frame level speaker embedding information. So later we will study the performance of these different the combination of the speaker embeddings. So here we can see if we use the single iteration performance like this, the target is the pre-enrolled. If we do a multi-run, then we can improve the performance. Then if we only use the frame level, which is we only use here, don't combine the here. So we also can improve the performance. But if we combine the utterance and frame level together, we achieve the best performance. So we also evaluate how is the performance if we give less duration of speech, enrolled speech. So here is if we have the long reference.
In addition, US West Data Solutions Business Applied Communications.
So here is the enroll of the speak. Here is the mixture speech.
The
Double
best
quote.
strategy,
I'm
comma,
sure of
he
it,
said,
period.
comma, is
Okay, so actually we want to check the male speak. Here is the effective speech.
the best strategy, comma, he said, comma, is
If we use a short reference, just 2 seconds.
in addition, US West.
Then we can also improve the
best strategy,
target
comma,
speaker
he
voice.
said, comma, is
So here is the comparison with the speech separation systems on the voice generated mixture database. So the red block actually is the speaker retraction system. So this is the frequency domain. These three are the time domain. Actually, these three is based using the temporal convolution networks, which is similar to this one. If we can using the improved network structures, I think we can further improve the performance of the speaker extractions. So here we also evaluate the performance on different scenarios. For example, in the noise case.
As part of the marketing plan, the company will begin airing television commercials during prime time.
This is estimated.
As part of the marketing plan, the company will begin airing television commercials during prime time.
So this case is to remove both the interference speaker and the noise. So this is a vibration case.
As part of the marketing plan, the company will begin airing television commercials during prime time.
Here is the estimate one.
As part of the marketing plan, the company will begin airing television commercials during prime time.
So here we are doing the devibration and the removing of interference speakers together. This case is we have the interference noise vibration.
As part of the marketing plan, the company will begin airing television commercials during prime time.
Here is that result.
As part of the marketing plan, the company will begin airing television commercials during prime time.
Okay. For previous case, we only consider the speaker is present. For example, this case, we have the target speaker A, which is present. Either has the interference speaker or non interference. So we have another case which is most of the time the target speaker may not talking, so we only have the voice of the interference. So how can we have a universal system to handle all of this case? Actually, we propose to use to design a loss function to handle this for case. Another one is sometimes because parental audio assisted speaker interaction, we need to have the voice of the target speaker as a reference. Sometimes we don't have this kind of information. How can we do speaker interaction? Actually, we also can use a visual. For example, when we buy a ticket using audio-visual assisted ticket machine, then we can use visual as information. Then because this system cannot ask the passengers to record a speech as in row, so we can use the camera to capture the lip readings of the speak. Then we can use this visual encode to get the information of the target speak. Then we do the extraction of this target speech. So after that, we further improve the performance by learn speech and lip synchronized network, which is we try to use self-supervised learning to learn this kind of information, because as we know, our when we are talking, we talk in different phones. Our lips are different, so we can have the synchronize the signals. Also, we simulate non-synchronized signals, which is we randomly shift the video and the audio to get this non-synchronized system. So with this system, we can try to learn synchronized features, which is capture the visual information. With the kind of information, we can do the speaker extraction. So based on this work, we can see actually the proposed visual assistant system, also the synchronized visual systems achieves better performance than the previous speech separation systems for both 2-mixture and 3-mixtures. So we also evaluate our performance on different data set, which means we train on Vox Celebra 2, then we test on real domain, which is LRS2 and LRS3. We also test on studio case. You can see our system actually robust to the unseen data set. So here is a demo between the debate of Trump and pattern.
I've already fixed it.
He has never offered a plan.
To an extent.
He has never done a single thing.
Know.
How to do that? He has never offered a plan. He has never done a single thing.
So here
I've
we
already
focus
fixed
on
it.
the
I've already
Trump's
fixed it to
voice,
an extent.
we only have the Trump's
Obamacare,
voice.
as you might.
So another case is when the visual is missing, how can we do the visual assisted speaker extraction? For example, sometimes the camera cannot capture the lip information. So actually, this work is proposed to do the visual information reconstruction. Actually, to do the embedding pattern to recover the informations missed. So another work is actually we talk about the audio assisted, visual assisted. Also, can we have some concept-based one? For example, we only have proposed some words. For example, these can words. Can we extract the speech of these two words? Then this work actually studied the environment sound extraction using automatic words by using the words as reference information to do the sound extractions. Here, this is similar. Actually, we have other different of concepts. We can say we want to have the female speech. Then we give the female labels. Then the output is female. We have the speech of the male. Then we give the male labels. We can have the speech of this male. So also we can say the speech far from the make. The language of the speaker is talking, also the loudness. Then we can give this kind of information. We can do different kind of voice ejections. Also, for the visual one, if we cannot totally don't have the visual information. For example, we have a mask taken to. We cannot, the camera cannot have the liver information. The embedding pattern works also fails. So how can we do that? Actually, this work study interest information is gesture. Actually, our gesture sometimes is corresponding to what we are talking about. So they design of different gestures using these gestures to do the speech detection. Here is the demo.
Is they make a cell phone, go down to the stall, they sell some, they look at the other kids' stuff, go up, make a couple thousand more, go down. And doesn't this sound like a software thing? It sounds like agile software.
The struggle to keep African narrative alive has been one of the most consistent and hard-fought endeavors of African peoples, and continues to be so. The struggles endured.
So actually from this demo, we can see the gesture information also can be used to do the ejection. Actually, it helps. Actually, previously we mainly talked on the single channel case. In this talk, actually, I don't want to include too much works on the multi-channel. Here I just give an example. If we do the single channel well, then we also can extend the work to the multi-channel, which is we do the speaker ejection with our previous single channel systems by adding the additional information of the special information, which is the direction of the target speaker. So we can do the network-based beamforming to reconstruct the symbol. Also for the multi-channel one, actually there are many works on this to do the using the network to do the mass estimation, then use the NVIDIA to do the beamforming. Also, they designed the GSM or the network-based beamforming. So if you are interested, then you can look at these papers. Before I say we talk a lot of works on speech separation and speaker ejections. So why do we do this kind of works? So now I would like to introduce some downstream tasks. We want to use the appropriate separation or ejection system to improve the downstream task. For example, the multi-talk speaker verification and the multi-talk speech recognition. So why do we want to have this speech separation or speaker ejection? system to speaker verification, because sometimes we have the scenario some of speakers are talking together. So for the speaker verification systems, if they all talking together, then we give this speed to the speaker verification to identify whether the speaker is the enrolled speaker. So it's very impossible, because the speaker verification system will have the unbundling all the characteristics of this mixed speakers. Then it's not easy to verify and compare with the enrolled speaker. So what we are going to do is to do the direction first. This is a try to do direction. But direction, it means we try to segment the speech without overlap, but they are shown in the same sequence. So we can do the direction to identify which segment is belonging to which speaker. But if the speech is overlapped, for example, they are overlapped in the spectral domain. So how can we do this? One is we can do the separation, then identify the outputs with the enrolled speaker one by one. Another work is we can do the ejection, because our audio assisted speaker ejection requires an enrolled speech. The speaker verification is providing the enrolled speech, so we can do the speaker ejection perfectly. So what we can do is we can use the enrolled speech of the target speech, do the ejection first. We get this speech, then we use this ejected speech compared with the enrolled speech again to do the identification or verification task. So actually in this system, we compared several different speaker ejection systems to compare the performance based on these two frequency domain and the time domain systems. After that, we also propose to use end-to-end system, which is we would like to train the speaker ejection and the speaker verification together. So here is the database we are going to evaluate on. So in the database, they have different percentage of overlappings. So the baseline is original system, SV systems. Actually, we train using the clean data. We evaluate on the mixture. We don't use the speaker ejection as a pre-processing, so the equal rate is very high. If we are using the speaker ejection system as a pre-processing, then we evaluate the performance. Actually, if our training doesn't see the ejection system, it can achieve improvement. If we add the ejected speech into the training, then the performance can be further improved. If we use better speaker ejection system, actually the performance can be further improved. So this outbound means we are training and the test on both on clean data, which is only one speaker is appeared in the input. So the performance of equality is 3%. Here is if we use the joint end-to-end training, which is we jointly train the speaker ejection and the speaker verification system, then we can further improve the performance. Okay, for the multi-talk speech speech recognition, actually, we have a lot of systems. Most of the systems are doing the overlap the speech recognition end-to-end. Actually, we have the end-to-end speech recognition systems. They combine the speech separation and the speech recognition together to do the multi-talk speech recognition. So I don't list too much of that work. Here I just show some of works using the speaker detection as a front end to do the multi-talk speech recognition. So this is a voice field line. Actually, they learn the speaker informations using a devector. After they train the devector, they do the speaker detection. Then after they get the ejected species, they use this speech to do the traditional speech recognition, where the speech recognition system is trained on single speaker. So in this work, they also proposed a loss function to solve the over-separation problem, because in our speech separation or speaker detection system, sometimes we delete or over-separate the sound frames of the target speaker's voice. So this work tried to try to design a loss function to penalize these errors, which is the separations. With this penalize then the speech recognition performance can be further improved. Actually, in the real-world application systems, this over-separation system is very serious. So we need to release the, for example, we can have the interference voice remaining in our output, but we cannot delete. So this is the case we are going to use as a constraint to our system. So another work is our work using to do the full band speech enhancement or speaker ejection with wideband ISR system compatibility. What does it mean is actually we have a wideband system for speech enhancement or personalized speech enhancement. Personalized speech enhancement is also similar to the our target speaker detection, which is we only output the speech of the target speaker. So we also call it as the personalized speech enhancement. So we have this kind of for example, our online applications already have this kind of wideband speech enhancement system and wideband speech recognition systems. So how can we keep this kind of systems and to generate a good quality of full band signals? What we are going to do is we use the actually we divide the full band speech into the high band part and the lower band part. Actually, we for the noisy remove, we still use our existing wideband system. Then we use this output together with the high band part to do the high band speech enhancement. Then we have the high band the enhanced speech. Then we combine them together. Finally, we do some post-processing to reconstruct the signals. So here we have several switches to control our systems. For example, if we want to have the personalized case, then we give the reference of the person of the target speak. Then we open this personalized switch. Then, if we want to output our SR output, then we send the wideband part directly to our existing wideband speech recognition systems. So this one can be used to have some advantage, which is we can use our already existed wideband speech enhancement system and the wideband speech recognition systems. So another work try to do is how about we using the visual assisted speaker detection system to do the SR. It means we use the visual assisted speaker detection to detect the speech of the target speak. Then we send it to the our SR system. So this will conduct some experiment on the SR case. Okay. Next, I would like to talk about the challenges still remaining in the co-party environment for the speech separation and the speech detection systems. For example, as we previously say, we designed a universal system to handle different cases, but this case is still very simple, just divided into 4 cases. Actually, there are some more. Then how can we improve the performance to handle all of these 4 cases? Because sometimes if we improve this case, then the performance in this case may be dropped. So how can we balance both of them? Also, if we add this case into our training, we find there will be some more over separation case. So how can we handle the over separation? Because the over separation is not tolerated in our real-time communication system. So another one is how can we have universal sound detection systems? For example, we have different sound, speech, music, bird singing, or some noise. So how can we combine all of these cases and using a single system to handle all of these cases to detect the speech of what we are interested in? So another one is in some cases we want to control the speech, the energy of the speech, the source. For example, we have the background music. We have talk, right? For them on the online video streaming. So we have we already play some background music when the anchor are talking. So actually, sometimes we want to suppress the energy of the music, but we still want to keep them. So one solution is we can separate the front end speech and the background music into different channels. Then we set a threshold to tune the energy of the background music, then combine them together. So this is just some applications for the universal sound detection or separation systems. Another is robustness. Actually, Professor will also talk about the 2 kinds of robustness. One is robustness to the environment. Another one is robustness to the languages. So Professor, we have the unsupervised pre-training and mid training. Also, we have the pre-training from speech enhancement system. We have the mixture IT system. But this kind of case I still have some problems. Another one is for the language generalization. Actually, we use a simple solution, which is we combine different languages to train a single system. Then we use this system to do different kind of language processing. But sometimes we need to know how can we how many languages as we need to have this kind of universal system. So we still need to study. Another one is I think is a real-time implementation. Actually, in today's talk, I mainly talk about the offline systems. Actually, some of them is not extended to do the real-time processing because the network structure limits them to do that. For example, the dual path or the iteration ones. It's very time consuming. Another one is actually in the device, on-device applications, our requirement is quite strict. For example, in this iPhone applications, we need to have very small number of parameters of the network. Also, the computing cost should be very lower. Also, for the hearing aids, we actually the requirement is even strict because this device has lower power, so the computation should be very small. So how can we, because if we design a real-time implementation by using small networks, then the performance of this network may be not as good as the larger one. So how can we transfer the capability of the larger model to the small model? So this is actually they have the teacher-student model transfer learning, but the performance may be not so good. So I think we still need to have some studies to do the real-time implementation. So okay, here are some of my supervisors and the collaborators for all the works. So that's all of my today's talk. So do you have any questions? Okay, do you have any questions? Okay, if not, maybe I stop here. Thank you for your attention.
Thank you.